A very good evening to everyone. I'm Dylan Ramanan, and I'll be the moderator for the day. We have gathered here today for the third session of the Isotopes Initiative. For those who are unaware of isotopes, it was started by the Society of Chemical and Process Engineering students, designed to provide undergraduates with knowledge regarding three segments which are key to a successful career. The first segment is a series of talks and discussions with academics and industrial professionals. The second segment is where undergrads are introduced to knowledge and facts which are interesting and govern the field of chemical and process engineering. And the final segment is a series of workshops designed to mitigate the gaps found between knowledge and applications. This is done through simulation softwares which are widely used in the industry. Coming to today's session, it's on the topic of mining. But hasn't mining caused huge environmental issues? Mining is a process that was developed by civilization thousands of years ago. They did this to find raw materials to build weapons and other useful tools. But mining didn't proliferate until the 18th century, when the world was introduced to the Industrial Revolution. In the need for a large quantity of coal and other materials, excess mining began, and along came the emissions. That's why we have Dr. Nilanka Ekanayake with us today to show us the ways of proceeding with mining with zero emissions through process transformation. And now, to begin with the session for today, it's my honor to introduce you to our guest speaker of the day, Dr. Nilanka Ekanayake. I am proud to say that Dr. Nilanka is an alumna of the Engineering Faculty, University of Peradeniya. After completing her undergraduate studies in 2016 at Peradeniya, she went on to do her PhDs at the University of Melbourne, where she did a research on microfluid cell separation. Currently, she is working as a research fellow at ARC Center for Excellence for enabling eco-efficient beneficiation of minerals at the University of Melbourne. Dr. Nilanka also worked as a teaching specialist and is currently collaborating with several universities on two projects with the Center for Excellence. And without further delay, let's warmly welcome our guest for today, Dr. Nilanka Ekanayake. Madam, the stage is yours. Thank you.
Thank you, Dylan, for that introduction. Can you hear me well?
Yes, madam, you're audible.
Okay. Yep. So first of all, a very good afternoon for all of you. Despite being a public holiday, it's really great to see the number of participants here from Sri Lanka, and also a very good late evening for the people who are joining from Melbourne for my talk. And give me a second to share the screen. Right. Okay. First of all, thank you for that lovely introduction as well, and also Scapes to inviting me to this series of talk, and giving the opportunity to discuss what I learned and also what I'm currently learning in this significant developing area of mineral processing. So today my talk is focused on different process transformation on mineral mining towards the goals of zero emission and net zero carbon goals to reduce the environmental burden as well as to increase the process efficiency. So first, I would like to start by acknowledging the center, the Australian Research Council Centre for Excellence, for enabling eco-efficient beneficiation of minerals. Firstly, to making me a team player and also allowing me to discover a very interesting topics that are very close to my field of expertise, and also to allowing us, all the researchers, to give giving a platform from researchers from different universities, as you can see, and also different industries and government bodies to come and discuss the underpinning issues behind mineral processing. Especially, I would like to thank the team members of COE Mineral Melbourne Node / group, and my former group, the Multi-Fluid Dynamics group, from the PhD students, research fellows, and technicians, and my senior supervisors, including Anthony, George, Peter, and Robin Dalton, for making a really good environment to work. And also would like to acknowledge the support given by the high performance computer team for even for PhD project and current my research projects for the technical support. So with that note, I will introduce or go through the outline or the major topics that I will try to cover or touch a little bit. So basically, the first thing we'll discuss about what is minerals and the difference between the minerals and the technology metals, and then the challenges that we are going through currently in this mineral mining process, and a little bit about the process, the unit operations, and the term beneficiation, which is a really tricky word there in the center, but it's really important. And also I would take you through 2 projects that I'm involved in, which has been designed to transform the process of this mineral processing, and a little finally would talk you a bit about the Center of Excellence in Minerals. Now, I would like, if you have any questions, please don't worry to disturb me. Just turn on your mic and ask any questions, or put it into your chat so I can answer at that point or later after my talk. Right, the first thing is I want to introduce a bit about minerals and technology metal, a little bit about the definition. So we are on the same page, what materials that we are talking today. So when it comes to mineral, usually it's a very basic thing, but we need to characterize, or we need to have some criteria to define and say, okay, this is a mineral or this is not a mineral. So there are these 4 definite characteristics. It should be naturally occurring, it should be an inorganic solid, and it should have a definite chemical composition as well as the regular atomic structure. So if these criteria are fulfilled, we usually call them as minerals. So these are a few examples. So as you can see, there are plenty of minerals, just with a very few which are some sort of familiar to us, and perhaps some might not be. So these are copper ore or copper minerals, where you can see the chalcolites or chalcopyrites, which bear copper metal, and these are nickel minerals, which has nickel in it. And then the very famous or very familiar ones are the hematite or magnetite, which has the ferrous in it, and then the calcite, which is usually known as calcium carbonate. So one thing we have to figure out is, among minerals, there are few metal bearing minerals and there are non-metal bearing minerals as well. So my talk would be narrowed down to metal bearing minerals, and as we will just refine our talk today towards these metal bearing minerals, rather than talking about any other calcium carbonate type of minerals. And for the audience, I have 2 questions. So please, I think there are a lot of students here. So just, can you answer these 2 questions? So a very simple, I think, to answer in the chat box is, diamond a mineral? Is coal, can we consider coal as mineral? So I would like to hear your voices. So can anybody say or just type in? Okay, I'll just wait 1 minute and I'll just see whether is there a very interesting student who is listening to this talk, and would there be anyone have a suggestion about this too? Dylan, do you think you mind stepping, or what do you think? Will other your colleagues will support you?
So yes, madam, there is a reply. I think the first
Okay.
yes, madam. So
Okay,
first,
one, right?
I also think it's the same, madam. I think the first one is a mineral and the second one is not a mineral.
Right. Okay.
Yes.
Yep. So obviously, I see there are a few couple of answers here in the chat box. Yes and no. And I think everyone, the people who answered it's correct. Yes, I will just go ahead with this one. So basically, diamond is a mineral. So it's the very solid form and the very pure form of the carbon. And it fulfills all these 4 criteria or characteristics. And whereas coal, so you usually call as bitumen, those are, well, it had the main component is carbon, but we have the secondary elements like hydrogen or sulfide, so where the presence of carbon hydrogen bonds make the coal as inorganic, organic, which therefore the coal won't be a mineral. So when we say mineral mining and coal, so we should distinguish that mineral mining and coal mining is a bit different. So basically, my talk will be on these inorganic solids, which is about not about coal mining, but mostly about mineral mining. But anyway, it has some overlaying areas, so we can discuss how these process transformations apply to each case. Now, among these minerals, so what I said previously was there are metals or metal-bearing minerals, but the interesting fact is there is some sort of called technology metals, which is often considered as relatively rare metals, which you don't have easy access for this and used in very high-tech devices. Now, it's not always the rare earth elements that I'm talking about, but it's about the accessibility. Now you can see this orange color, the indium, the niobium, or the cobalt are usually considered as tech metals, whereas the ferrous or iron or aluminium is generally considered as industrial metals. So these orange color metals are like extracted in very low quantity, whereas the industrial metals and are extracted relatively in a larger quantity. So I have a nice figure in the next slide. So this is a graphical illustration of the amount of minerals that we had extracted during 2019. And these are the sources for this image, which I adapted from this website. But it's a good depiction, or it depicts the amount that we mine per year. And, you know, it's around 3 billion tons of iron that we have been mined for 1 year. And you can see the other, compared to this material, the other materials like aluminium, copper are relatively low. Those are still in metric tons, but still relatively less than iron ore. Whereas in this case, these rare earths and the some other things like there was a gold, silver, those type of metals are extracted in extremely very fine quantities or very small quantities compared to the other elements. So, you know, with this figure, we can have some understanding about the amount, what metals are extracted and in which quantities. Now, saying that, the other one is, okay, so I said these tech metals that will be used in your devices. So one of the device that we usually, I guess now everybody has is the smartphone, and interestingly, it's very useful nowadays due to this COVID situation, where you can use the phone to access your slides or any educational materials, I guess. And then the thing is, if you're using your smartphone, so it's like roughly 60 metal, you're consuming 60 metals. And then it's interesting to see like touch screen, which should have a very high conductivity to have the sense and create that electric pulse. So you have to use indium. And and then the display, to have a clear display with crystals, you have the rare earths in the display. And then in the storage battery, obviously we have lithium, cobalt, and nickel. And even in the diaphragm of the speaker, you will have nickel and some other metals. So you see, like, you are combining different type of metals which are extracted from ground and using your smartphone. Now, what's more triggering or a little bit alarming is the study of Yale. They have the statement in their final report, which says, okay, there is unlikely there is a good substitution for these metals. So basically, we have to stick with these metals in order to have a smartphone. But there is a challenge in mining these metals. So we need to go we need to use these devices, but still there is a problem looming because of the substitution is not that good. Like, it's not there are no potential substitutions at this stage. So that's a very alarming thing. Now, another thing is you use different materials in the medical technology. Now, some people's lives depend on certain medical equipments, and also the hygiene of the equipments that you use. So based on the antibacterial and bacterial resistant property of certain devices and certain instruments that you use, especially in the copper, the amount of copper you use in MRI is really large. And then you use titanium in surgical equipments and silver in antibiotics to promote silver is used as medicinal in the antibiotics to get the required amount of medicine to your body more faster than the normal antibiotics. So you use these technologies, but also apart from that, you use a number of metals or tech metals in medical implants. So whether it be a cardiovascular implant, dental implant, or simply a knee or a hip joint, implant, you use this rare earth elements, as well as like some metals or tech metals like chromium and silver, gold in these medical implants, which some patients' lives depends on it. So it's critical to have these metals in our use. And then the other thing that we use this mineral or the high-tech mineral is for the low carbon technology. So this is a nice graph, or like I said, nice table, which says, okay, people are supporting for low carbon technologies like solar, wind, and also regarding the energy storage, or so they're going for these electrical vehicles and batteries. So you can see the amount of, or not the amount, actually the type of metals, the quantity of metals that they need. So this is a qualitative depiction, but you can see you need copper, nickel, lithium for these batteries, and also you need rare earths elements for these wind turbines. And to give you a quantitative idea, so you can say, so like we need lithium and nickel 30 times as we use by now. Like in 2014, we need lithium and nickel 30 times as much as we use now, and for these only for the electrical vehicles. And by 2023, the growth of solar and wind will increase by 70 to 60%, which will need a massive amount of copper, silver, tin to produce these equipments and to transfer power, transfer energy from one location to another. So, okay, so I've established the fact that yes, we need minerals for different things in our life, but there is no good substitutions specifically for certain metals. But what are the challenges that we are facing? That's the question, right? So basically 3 challenges I can just point out. So that's skyrocketing demand, which is increasing demand, and low ore grades, and the tailing storage management issues. Now, the first one, which is very familiar with listening to the previous video, because it's fine if we have a demand, it's whether it's exponentially growing or not, but we have limited resources. On the other hand, the other issue is the low ore grade. So I would like to so maybe we're not familiar with the term ore grade. So grade of a ore is the index or the amount of concentration of the desired material, in this case metal, which ore contains. So let's say you might have 0.3% copper ores or 0.5% copper ores, but unfortunately the percentage is getting reduced because we have access all the fine ore grades. Now we are going for these low ore grades in this century. So the thing behind, or the challenge is, since the ore grade is reducing, or the concentration of that the rock that we take from the ground it's very low, we have to put a lot of energy and water to recover that metal, and therefore it creates large amount of waste because we extract large amount of rocks which are not really needed to further process. So that is the main issue. Then because of this, we are generating large tailings. So that is, tailing is called this waste product which coming out of minerals, mineral processing. Now the tailing is if we do not manage it well, so that is sometimes it creates catastrophic disasters, and sometimes it has killed many people and also affected our ecology system very badly. So we have to address these challenges, and I will just give you some numbers for the demand. So you can see these 3 bar charts. So the first one, it shows the lithium consumption. It's in kilotons lithium carbonate equivalents. So, and it is forecast, the report is generated in 2020 by Australia, and it is forecasted from 2022 to 2030 and 2040. So you can see this exponential growth of lithium ion batteries, and in numbers, it's like 368% growth. Now, it is a massive amount, right? And then the rare earth element. So this is a neodymium, one of the rare earth element. So it's like a 3-fold increase from 30 kiloton neodymium oxides, and it has increased 3 times, like up to 90. It will be increased by 2040. So it's another challenge, because the availability is very scarce. It's very rare, as the name implies, right? And in terms of copper, it's not in kilotons. Look at the scale, so it's in megatons. Sorry, and the rise is like 10 times metric tons from 2019 to 2030, right? So obviously there is an issue with the demand, but the thing which a little bit scares us is this graph. So the demand versus supply, whether we can match that demand. So this is again another good report from the Institute of Energy Authority, and these 2 lines. So these 3 graphs represent copper, cobalt, and lithium demands and supply. The line graphs shows us the predicted demand based on 2 different scenarios, with introducing 2 different climate like sustainable policies, and the blue color graphs, or the field colored graphs, shows us the amount of resource available, which is either operating mine or under construction. Now, in any case, we see a deficit, right? So demand does not match the supply. Sometimes the supply will go down by 2030, especially with copper. So there is a huge challenge where we are facing, because we are introducing, in one side we are introducing low carbon technologies, but on the other side we are using a lot of metals to develop these low carbon technologies, but we are losing this availability of the resource. Okay, and then the other one is the ore grade, which means the concentration of the metal. So this graph is a variation by years, and the y-axis represent the ore grade as a concentration for different metals. So the general trend of all these metals is declining, right? So for example, if you take 1855 copper, if you get 100 kilos of copper ore, you will recover 20% of copper from that. But now, if in 2005, if you get the same copper ore, like 100 kilos of copper ore, you will only get 2 kilos. So, you will generate large amount of waste, and also you will put a lot of effort to extract these minerals or the required metals from that ore. So this is another issue that we are facing. Now, this current data is based on Australian data. So one might argue, okay, it's a localized problem in Australian mines, but I want to show you that it's not a problem with the geographic or anything. It's happening globally. So this is the copper grade declining in different countries. So you can see it would be a really challenge for not only for Australia, but for the entire world, this declining ore grade. Okay, so just to re-emphasize, this will cause these two effects. Now, this is some sort of a graph which shows the economic resource. So this is kind of an index which we use the energy and water consumption. Now you can see with increasing from past to present, or 2010, the amount of energy or the cost for the resources, for the energy and water has been increased, because we have to go through multiple stages of processing through the extraction as well as processing. The number here, like let's say if you need 30% copper concentrate from 0.5% copper mineral ore, you have to put 60 megajoule per kilo. But if you need to have the same 30% copper from 0.3% copper ore, you have to put 450 megajoules per kilo. So a slight change in the ore grade will require a large number of energy to put in. Okay, so basically declining ore grade is another challenge that we are facing. Now, with that, so we take the little bit of metals left there and we remove the rocks, but we can't just put in those rocks in a landfill area, right? You have to send it to a tailing management facility. Now, the quantity that we have generated so far is like 217 cubic kilometers. And this graph is, again, I thought it is really nice because this is the Manhattan city, and if you put all these tailings or the unwanted rocks, you can make 6 by 6 cube of tailings, which is like 282.5 billion tons. And each year there is an addition of tailings for this chunk. Now, it's a huge problem for this landfilling, because we cannot let it sit somewhere in the land after we mine. If you use a pit, like mining pit. And so now the question is how to address these challenges. So obviously through a process transformation. But I would like you to read the first part. So I would say apart from policy changes on consumption and population growth, because there should be some common sense and at least policies to say, talk about the consumption. If you are going for excessive consumption, it's very hard to control the demand, right? So people should think a little bit on that note. But as engineers and researchers, what we can do is transform our process and increase the metal recovery and reduce the water and energy consumption. Now, for that, we have to understand the mineral process and beneficiation, the flow chart as chemical engineers. Now, this is just a very fundamental, very simple schematic. So you mine, then you grind, and then you concentrate or dewatering, that is what the beneficiation part calls, and you smelt and manufacture. Although it looks simple, it involves many number of unit operations. So you see, this is the crushing and grinding unit operations which usually use, and this is the dewatering unit operations in the beneficiation process that we use. So in our center, we are more focused on beneficiation, but not limited to looking at comminution as well. But my study is more towards beneficiation and dewatering. Look at the beneficiation part only. So you sell the comminution from the grinding, you get the ore slurry, which has high amount of water and grounded rocks, valuable minerals. So you send it to this flotation cell and separate tailings or the rocks, and then from the valuable minerals, and these tailings are sent to these management tailing facilities such as these dams or the tailing ponds. Now, the problem here is you have low solid concentration or very dilute fine particles going to this tailing management facility, which you don't want because it causes these catastrophic disasters because of the pressure, the solid pressure it contains. So what we need is to dewater tailing before sending that to a tailing management facility. And in the next stage, we do a concentration by thickening or filtration. So you remove excess water and then send these minerals or metal-rich slurry to the further processing, which is a concentration. For each case, you could see either it's a solid-solid separation or it is a solid-liquid separation. So I think for this transport phenomena, we are looking at the solid-liquid separations in your courses, and we use those fundamentals in creating these different equipments. So this is generally called dewatering. So we use different equipments based on their particle size, slurry contents, concentration, volumetric feed, and the operational cost. So for example, you might use a vacuum drum filter if it is the dilute suspension and you need a very low throughput, whereas you might use a thickener if the suspension is dilute, but you can manage a high throughput from it. So we are dealing with this micron range or like micron range particles, and we have to deal with these equipments. Now, the framework, or my work here is to understand the physics behind this and how the momentum transfer works, how the mass transfer works. So for that, we are using this Baskel and White compression rheology framework, which has two key parameters. One is compressive yield stress. So you have a solid network, you apply a load, so you remove water, but after a critical yield stress, this network fails. So that is a one parameter to measure the dewatability, and then the hindered settling rate, which is about the permeability of suspension. So we use these parameters to model mineral suspensions or tailings in such case, which has this calcium carbonate and etc. So we can't treat this mineral any type of suspension as more single phase because we can't separate solid and liquid. So in order to model or simulate, we use this two-phase approach. This is some sort of work that I've been doing in this center. So developing equations to treat this solid liquid separation and estimate how we can dewater, how we can increase process efficiency. Now, I don't want you to go through this equation, but just to say that, yes, we solve for two phases, fluid and solid. We solve the mass balance, we solve the momentum balance. And these two critical parameters, the Py, which I mentioned earlier, and the hindered settling functions are used in this equation. So basically, this is not a one-dimensional one. This is a three-dimensional equation which has to have X, Y, Z directions. So we are working in tensorial environment in order to combine the experiments with some sort of maths and physics. These are a few very preliminary results that we are trying to generate now. It's about this. The first graph is the height of this interface variation. You can see when the settling happens of the calcium carbonate 40 micron particles, and we're trying to match with the experimental results using the simulation. So if you know the maths right of what's happening in physical world, so we can expand that to different devices, although here it is just a settling column test. And the second figure is the height variation versus volume fraction, so which is another important parameter which we cannot measure visually at this stage, but from using CFD simulations we can do, and if we can validate it, we have the ability to understand the load like the pressure created in different vessels and etc. Now there are two projects. I think I'm running out of time. Am I, Dilan? Or
no, madam, you can continue, madam.
Okay, just four slides. So the process transformation. So I will just quickly go through with the projects. The first project is about how to apply pressure to dewater, and we are looking at a new equipment which is called the high pressure dewatering rolls, which has been previously used for different other suspensions like paper pulp and wastewater sludge. Now we are looking to apply this new technology, which has been developed by University of Melbourne by a team, to whether we can use that for mineral tailings and whether we can model these suspensions and whether it's cost effective and a pathway to commercialize this equipment. Now, just to give a brief overview, so this is this equipment. So we have a chute, we insert the tailings, and this is the permeable drums which are rotating. This could be synchronous or asynchronous, which means like a differential rotation rates, but this is like acts as a filter, and this has a vacuum pressure, so they suck water and we get very concentrated cake out of this the nip here. Now what we do is, by using that equation set, we try to model this HPDR so we can have some optimum conditions. And the challenges are, this is not a monodispersal, have very even particle sizes, so we have to address that. And also we have to look about the pressure development in these rollers. So that's one of the project, and there's a huge team behind this one. It's a lot of feeding to this project in different aspects, experimentally, theoretically. So I'm doing the simulation side, whereas Sajid, the PhD student, is doing the experiments, and also there are a lot of team members working on this in mechanical side as well. Then the dewatering of the other project is dewatering of small hydrophobic flocks. So forget about the topic for the time being, but you see the pressure curves as a very function of solid concentration. So if you have small particles like 1 micron particles, so you can see your pressure at the gel point here, which is usually called the pressure which starts to accelerate after a certain volume concentration, is much less than the 40 micron one. So if you have fine particles in a suspension, it has a lower gel point, which says it cannot withstand large applied loads. So it is not desirable to have fine particles in tailings, right? So this is another graph, which is a function of height versus time. So you can see the fine particles are settling very slow because of the Stokes law that you might have been using, but large particles settles faster. We need to separate these solids and liquid faster. So having small particles is not a good thing. But what's happening is, since the O grade is decreasing, we have to crush and crush. So the particles are really fine. Now, what we try to now, if we send these fine particles to tailings, it has more a tendency to the dams to fail. So before sending fine particles, what we try to do is aggregate them. So make the particles large, so the settling and the separation happens much faster, and it can withstand certain higher loads. So, so we are here in this project. Yushan's doing is to use an emulsion, or not a flocculant, but an oil emulsion to agglomerate these particles and see the particle behavior, and also see the effect of dewatability. Now, these are the two projects actually that working towards to enhance the tailing management facility, which is one challenge, and the water reduction in the HPDR, which is another challenge. So that's how we try to work out those challenges I listed previously. Then a little bit of ARC Center. So basically, these are the main goals: to double the energy and water productivity in mining sector, and reduce the loss of high valuable metals, because we don't want at least a bit of metal to be gone to tailings. We have to recover much as possible because the resources are limited, right? So then the last one, which is I really want to emphasize, is establishing a new generation of scientists and research, which is a really good thing, which I personally like, is creating, passing the knowledge to the next generation. So we have this knowledge from the experience from our previous scientists, and now we are trying to work with the new technology to enhance towards that. And this has been done in 3 programs. So you can see a lot of details from this website. So you just go, if anyone's interested of doing any type of research work related to hydrodynamics, or any chemistry side research, or polymer side research, there are 3 programs running. And if you have interest, you can go, and there is a portal that present your expression. So, and also you can contact me if you go through this. There are a list of projects under these topics, and I think you can go through that as well. So I will end my talk. Sorry if I took a little bit of time from the Q&A session, but thank you very much, everyone.
Thank you very much, madam. That was a very perspective address to our topic today, zero emission mining through process transformation. Your presentation was very fascinating and stimulating, and I'm pretty sure everyone learned a lot today, a topic that is very alien to us. Thank you for that, madam. Now is where the two-way process begins. Time for questions. I know many of us would have questions regarding the topic spoken today. This is your time to clarify them from a person who is well educated and experienced in this field of study. You can raise hand and we'll call out your name to ask questions, or else you can drop a message in the chat box and I'll narrate them out to Dr. Nilanka. I hope everything is clear, and now it's your opportunity to get your doubts and gaps clear to further enrich the knowledge you have gained today. Thank you. So, madam, can I begin with my question? So, madam, we were talking about mobile phones and like lots of electronic devices having rare materials, and those are like really like hard to mine. So, how about recycling them, madam? Are there methods of making use of? Because I think electronics usually have around 5 to 10 years of lifespan. So, is there any other way of effectively removing the indium from the screens and other chromium and other metals from the waste?
Yes, actually a good point. And there is an interesting paper which I read like yesterday night on recycling the, I think it's recycling the battery, like a few minerals in battery energy storage sector, but still, and I will send you that paper which has predicted the demand. So instead of a growing demand, it will have a like a sinusoidal wave, but still it will still increase. So basically you will have because of the recycling, there will be a dip, but that will increase after like a 10 to 15 year gap because of the usage again. So obviously there are, although that is not my field of expertise about recycling metals, but there are current trends on thinking of recycling, but even with recycling and still the demand has been predicted like some sort of a logarithmic or exponential growth, even with the fluctuations. So yes, there are research going on in recycling, but still you can't meet that or the demand from the current resources that we have.
Thank you. Anybody else can ask your question, or you can drop a message in the chat box and I'll be able to narrate it.
Can I ask a question, Dylan?
Yes, sure, sir.
Right. Thank you, Dr. Nilanka, for your insightful talk. Actually, this question pretty much related to experimental aspect in the ground level. So I'm a little bit curious about, I mean, in your industrial scale, what sort of, the techniques, characterization techniques, like how routinely you do these techniques, like when it comes to the materials, like for example XRD and other like quantification of different elements using high-end techniques. So like, is it like routinely carried out, or I mean, is it like playing a major role like in your projects?
Yeah, so if I understood your question correctly, so the material characteristics are continuously performed, especially more than in universities. It's been doing on in the industry, but also we are getting sometimes some universities getting mineral samples which has to be go through this material characteristic process. So obviously the apart from imaging and using imaging, there are different imaging techniques, and also the so I'm looking at more about the dewaterability. So there are a couple of different other characteristics related to the physical quantities. So we are doing, since we are getting the minerals and the materials, so we are running in our equipments, not as regularly, but if they need, they will be sending the materials and we'll do that. Is that the...
Yeah. I was curious about material aspect. Right.
Okay.
Thank you. Thank you, Dr. Thanks.
Yeah, I have a question, Nilanka. It's Charita. So when dewatering, what is the moisture content range that you are working
on? You mean after dewatering?
No, before, like the original
so
moisture content of the tailings?
Tailings, that range usually like like solid concentration. I will talk in terms of solid concentration rather than moisture, but so it's like around like 1% to 2%, like it's a very dilute suspension. It has like, you mean the solid concentration is very low, sometimes it is less than 1%, the solids. So we are at least trying to go up to like 40%, 50% solid concentration from 1%. So that's kind of the target.
Okay, so like this very dilute solution, is it directly sent through the rollers, or do you have a concentration step before that?
No, so right now for the HPDR, we are sending like 6% solutions of minerals. So although it look like 6% looks like feels dilute, but when you see the actual sample, which I don't have a picture of it, but it's looked very thick, even it's 6%. Yeah.
Okay. And one more question. So you mentioned that you use a emulsification technique for coagulation, right?
Yes, like yeah. Well, particle aggregation, yeah, because yeah.
Would you be able to explain like what? I don't know if it is your expertise area, but
I will say so. Either you can use a flocculant to aggregate the particles, like it's the most common thing to do, like increase the particle size by combining particles using a flocculant, so which is called the flocculation. But here we are looking at aggregation rather than flocculation. So we use like a emulsion to aggregate, so which the developing emulsion is not like, it's kind of testing by Deakin University, and also by our PhD student who is from the chemistry side.
Okay.
Now, what happened is the part, like what we're trying to do is, once the particle aggregates, so we try to pelletize them to make more solidified particles, so we can have much higher dewatability, which we expect, we haven't tested yet, but have much more higher dewatability than the flocculated particles. Because the problem with the flocculation, the structure, which is arranging, it contains water, large amount of water within that flocculant. But that is not desirable for the tailings. If it goes with large amount of water, that particle, that with particle connected with that flocculant, it will create that tailing dam issue. So we try to repel that water which is trapped in the aggregation process by using that emulsion.
Okay, Nilanka, thank you.
Yeah.
Anyone else? If you have any questions, you can ask or drop it in the chat box. And so university, yes, madam. You can ask. Yes, you can ask a question.
I am to share here. Then all these separation processes are physical.
Yes. So the processes that we are currently looking is physical, but the flotation device, that there are a huge number of projects going on the flotation area. So those are actually chemical related, like the selectivity of the particle to attach to that bubble. Yes. So whether it's the hydrophobicity, the hydrophobic or the hydrophilic particle, and how to increase the hydrophobicity. That chemistry, the chemical separation side is also there in the other projects, but I am looking at the physical separations mostly.
Okay, thanks.
Thanks.
So if we are done with mining questions, I think University of Melbourne is one of the top 3 universities in Australia, and I think you can ask questions about higher studies as well, if madam is okay with that. Madam, will there be a problem about if some students ask you questions about regarding higher education?
No, sure, you can go ahead, and I will share whatever I know with you. So obviously, I think just, if you're interested in the mineral area, so there is this opportunity in the center, which is also combined with different universities. But other than that, I can comment on the chemical engineering department, University of Melbourne opportunities.
Yes, madam, that'll be good.
Yeah.
So if any students, yes, you can ask away.
Is possible.
Yes, madam. Madam, as I know, madam, in Australia, this mining industry is one of the most highly celebrated industries, and there's a different set of engineers known as mining engineers who are specializing in this field. So my question is, madam, in addition to research and development, what are the opportunities do chemical engineers have in this field, and what is the difference between this mining engineering and chemical engineering?
Yeah, it's a really good question, actually. So there is actually undergraduate pathway as mining engineers, which are specifically trained to work in mining. But of course, there are a lot of flavors of mining engineering in chemical engineering, because, you know, throughout our 3rd to 4th year, I think we are learning a lot of solid and liquid separation devices. So transitioning from chemical engineering to a mining engineer is, I think it would be really easy. So there will be a little bit, a little bit catch. So if you are coming as a, rather than a researcher, if you are industrial, if you like to work in industry, there might be a little bit challenge. But of course, any experience in industry which related, if you dealt with any solid liquid separation unit or any unit operation in a real industry, that experience will be taken into account, no matter whether you are a chemical engineer or a mining engineer. And so the experience, it will be really good to have some sort of experience. If not, your internship, if you work in industrial field where you really work any in related to this, any equipment or process or any type of like sustainable management systems, because the tailing management systems, it's a different area which is not directly related to mining engineering, but you have to have some management skills in that as well, because it's dealing with a lot of people. So whether you're a process control engineer or any, you can name any, you can have any title, but the experience would really matter, I would say. So if you can, if you are interested in doing any work in industry in this mineral section, I would suggest pick the internships or in like the internship or the industrial training in industrial plants in Sri Lanka. So you have some exposure to the amount of work, the loads, actually, because you are dealing with metric tons and etc. So you know the capacity, you are familiar with that, and so you have something to present to the interviewer.
I got it, madam. Thank you, madam.
So, madam, I have a question. So, how is chemical and process engineering in general? Like, if I had education in Australia, is it like how good is the facilities and everything, madam, when comparing it to the US or the UK?
You mean for the research purpose or?
Yes, madam.
Universities? Yes. Yeah. Now I would say it's usually there is this comparison between different regions or different countries, but I would like to emphasize it really depends on the university, rather than whether you say it's a USA university or Japan university or Russia or any place, but the university matters, I think. And apart from that, the field of study, you have to, like, for example, if you are dealing with food and biotechnology or mineral, so it is currently happening in Australia, and you know there are a lot of industries, like world leading industries are there in this country. So obviously these specific fields are really good in some universities, like the research areas. But if you are looking at the technology side, or let's say, I don't know, if it's say like optimal, like where you, because we don't produce much amount, like the it's not chemical engineering, but it's example, if you are doing some software engineering or related to any codings or anything like computation person, so obviously your area, like you should check for Singapore and USA areas. But so I won't say, I can't compare this is good and this is bad, but I would say choose your field first. So there will be a field that you like very much, and then figure out what are the best industrial, like what are the best industries for that field and where are they located in which countries, and then go for that university rather than checking the university and coming the other way around. I think like that would be a good approach in a way. So yeah, so I mean, in for example, Melbourne, it's very good, like the different biotechnology companies are there. So obviously there are huge potential opportunities for food and pharmaceuticals, whereas Queensland, there are a lot of mineral related research is going on. So they have equipments, a lot of equipments there in the Queensland universities for the mineral processing. And so if you are interested in that area, you can check for those universities, but also always you have these collaborations as well. So it's up to you to decide. So even within Australia, I feel like certain areas, geographic locations are popular for certain industrial products, and the universities are have the similar trends. Did I answer your question?
Yes, madam. That was very helpful, madam. Thank you very much. And we can wait for another 1 minute. And if there are no questions, we can move on. So if anybody has any other questions, you can ask. This is your time. Madam, I think we are done with questions. So thank you very much for answering all the questions and teaching us about new concepts present in the field of chemical and process engineering. Now I believe that our audience have a complete idea about the concept of zero emission mining, and we might have gained a lot about research and higher education as well. And now I would like to invite Ms. Chirangshri Ihalavithana, the event co-chair of isoTalks, to propose a vote of thanks.
Thank you, Nilan. Good evening, ladies and gentlemen. Please and acknowledge the contribution of everyone, those who dedicated their time and energy to make today's event a successful reality. First, I would like to express my gratitude to our guest speaker, Dr. Nilanka Ekanayake, for not only sparing her invaluable time for us to grace this occasion, but also for enlightening us with a commendable talk on the subject. Thank you, madam, for putting in your best effort to make this event an unforgettable one. Special thanks goes to Dr. Charita Gamlat for coordinating our renowned guest for our session today. Next, I would like to thank our beloved academic staff of the Department of Chemical and Process Engineering for their valuable contribution and encouragement in all our efforts. Last but not the least, I thank all the participants who joined us today and the committee members of SCAPE, without whom this event wouldn't have been a success. Thank you all for your attention and stay safe.
Thank you, Shirangsi. Now we come towards the end of a fruitful session. I hope everyone had a wonderful time, and I would like to thank Dr. Nilanka for making this session happen. Thank you all for joining today and making it memorable. So with the hopes of meeting you all again with another interesting topic, it's time for us to bid our goodbyes and wrap up today's session. Thank you, everyone. Have a good night and stay safe.